All right, so I'll introduce our speaker. Our speaker tonight is Gina Duggan. Gina is from Ventura, California, and she's managed to stay in Southern California ever since. She did her undergrad at the College of Creative Studies at UCSB, and she's now a graduate student at Caltech Astronomy. Her research interests are galactic chemical evolution, stellar evolution, and instrumentation. Aside from astronomy, she also likes quilting and painting. So if you have any questions about quilting or painting, or obviously about her astronomy research, then come find her afterwards, and I'm sure she'll be happy to answer. All right, so let's get the show started.
Thank you so much for coming. I'm so excited to talk to you today. So as Michael said, I'm a grad student here at Caltech, and I'll be finishing in just a couple months with my PhD, so I'm very excited about that. Thank you. And so I'll be talking today about my thesis work. And so I work on galactic archaeology, which by the end of this talk you will be experts in. And it's digging through the remnants of galaxies. And so this background slide that I have, you all probably have seen because it's one of the most famous images. And it's the Hubble Ultra Deep Field, where all of these dots, with the exception of this one, is a galaxy. And so this image occupies 1/80th the size of a full moon, so it's very small. And it contains 10,000 galaxies. And so every speck you see is a galaxy. And so the smaller galaxies are further away. And people say, or people have discovered, that these galaxies go back 13 billion years. And so we're not quite seeing the birth of the universe, which is 13.7 billion years, but we're looking back very, very far. And so today we're going to talk about galaxies, why we study galaxies, how can we see galaxies change, galactic archaeology, and an example of using galactic archaeology, which is my thesis topic, and specifically we'll address where are heavy elements made, such as gold. All right, so I wanted to start broad. They say start broad. So what is in the universe? But then when I thought about this more carefully, this is a complicated question because there's energy and time count as in the universe. So what I really want to talk about is what can we see in the universe, which is a much easier question to talk about. And so first of all, we see galaxies, right? We looked at this picture. We saw galaxies. You can see galaxies in the universe. Galaxies have stars, such as our sun is a star. And some of these stars have planets, such as this is Saturn, but Earth is also a planet where we live. And so we live in a galaxy called the Milky Way. And so galaxies have stars and planets. They also have dust, which is hard to make a cartoon drawing of. So we have some dots to represent dust. And when you look at a picture of a galaxy, you'll see intricate shaded regions, and that's dust. And so dust, in my opinion, makes images much prettier than if they weren't there. But they're also a challenge for most astronomers. But we're not going to talk about that today because I don't care because I look at stars. And then there's gas. And so here we have a little gas whooshing in some direction. And so these are the three main things that are inside galaxies. The universe has 200 billion galaxies. And I always personally like when I take a step back at my research and realize that astronomical numbers are really, really big. And so I'm sure you've seen something similar to this, but we're going to think for a second about how incredibly large 200 billion is. And so the thickness of a human hair, so if you look at your hair, the thickness of that is 0.1 millimeters. And so if you had 200 billion hairs side by side, so if you stacked up their thickness, this would fly you almost halfway around the Earth. And it's equivalent to the distance to fly from Los Angeles to Cape Town. And so anyway, so 200 billion is a lot. And as you'll just keep in mind throughout this talk, that when we talk about astronomy, when we talk about how big a galaxy is, they're just, everything's incomprehensibly large. And so we're talking about galaxies. One reason why we care about galaxies is there's just so many of them. There's 200 billion galaxies in the universe. And how galaxies are created, grow, change, and die impacts all other areas of astronomy. And so this is because if you are studying cosmology, if you're studying the large-scale structure of the universe, you use galaxies almost as pebbles. You track how they cluster, you see how they rotate. They are your experiment space. And then if you study something smaller than galaxies, they live in a galaxy. And so therefore, galaxies are important. All right, so now we have committed ourselves to study galaxies. This is what we want to do. But we cannot design an experiment and alter a galaxy. So in almost any other area of physics, you're able to design an experiment to test something that you want to understand more of, and then you do that experiment and look at the results. In astronomy, we do not have that option. I cannot control a galaxy. I cannot decide to do something to a galaxy and see it change. All I can do is observe. So we often, astronomers call ourselves observers. We observe the universe, we see what happens, and then we try to backtrack to see how that happened. What does that mean for our larger knowledge of physics? And so here's to, you are here. They have T-shirts of this. And it's just like, there's nothing that we could do. Even if we managed to blow up the whole Earth, the universe would not care. And the galaxy wouldn't care either. I would care. But, okay, so we want to study galaxies, but we can't design an experiment to change them. And galaxies on their own change very slowly. So we can't observe a galaxy change in our lifetime. So the quickest time scale that I could come up with, the quickest thing that happens in a galaxy is a massive star dying, which takes 3 to 4 million years. Everything else is measured in many millions of years or billions of years. And a human lifetime is 0.0001 million years. And so the time scale that galaxies evolve is way larger than anything that we could possibly see. And so we need to find some way to not control galaxies and to not actually see them change in real time, but to still study how galaxies change. And so we do this with galactic archaeology. So galactic archaeology was coined because scientists thought that digging through the chemicals contained in young and old stars currently alive to picture how the galaxy has grown is similar to archaeologists digging through and seeing the remnants of people that lived before us and trying to piece together what happened in their lifetime and how times have changed since then. And so instead of looking for relics of a past civilization, we're looking at ancient stars and seeing what has happened to them, and from that, what can we say about galaxy evolution as a whole? An analogy that is more intuitive to me is that galactic archaeology is a little bit like psychology or sociology to me. So it's similar to asking people alive today about their childhood and how that would tell you how the world has changed over time. And so if you asked me, my mother, and my daughter about our childhood, you would get an idea of how the world has changed in the last 60 years. But instead of asking people alive today, I am measuring stars alive today. And instead of probing 60 years, I'm probing billions of years, because stars live a very long time, especially lower mass stars, like our sun. And so this analogy you can take a step further, because not only so you would also have a selection effect. So if you asked me, my mother, and my daughter, assuming my daughter could speak, we would all tell you that for Christmas, we have spaghetti. Christmas morning. That is our Christmas lunch. We would have spaghetti. And so you would conclude that all humans in the world, their childhood involves having spaghetti on Christmas. And as you might know, that's not true. That is true for one family in Southern California. 3 women say that they had spaghetti on Christmas. And so that's a selection effect. It depends on what group you're talking to. What stars I measure impact what results I have. And so you'll see later in my talk that I'm not talking about how all elements are made in all galaxies. I'm talking about how one element is made in small dwarf galaxies in the local volume very nearby when they are young. And so all of these qualifications are a mouthful and may be frustrating to hear me add so many qualifications, but that's what I'm studying. I'm studying young dwarf galaxies that are nearby. And so similarly, I wouldn't want to claim that asking these three women tell you about everyone's childhood. You need a diversity of measurements in order to say anything about that. Okay, so I keep talking about how I'm going to measure chemicals and these stars and how they change over time. But first, let's think about why do chemicals change in a galaxy over time at all? So when the universe started, it was, we call it pristine. It had hydrogen, helium, and some lithium. And that's it. Everything else, every other element you can think of, came from stars or explosions or mergers involving stars. And so if you started out with a clump of gas, which my cartoon shows here in a spiral pattern, you have stars that form out of that gas. And so like how a person retains the childhood memory of when they were a child, the star retains the chemical composition of when it was born. And so as the chemical composition in the galaxy changes, the chemical composition in the atmospheres of the stars that I measure changes as well. And so stars form out of this gas. At the same time, we have pristine gas, so hydrogen, helium, some lithium, flowing in and diluting the chemicals that are currently there. Just like if you had a concentration of orange juice and you add in water and it gets lighter, it dilutes it. And then you have stars either exploding or merging and releasing the chemicals that they have formed throughout their lifetime into the galaxy. And so that enriches it. And all of this stuff happens at the same time. You get gas flowing in, diluting, you get gas being emitted from stars and enriching, and you get it all mixing up. And so this is galactic chemical evolution, is this process. And so the main takeaway is that over time, galaxies become richer in metals. And so over time, the ejecta of stars, what the material the stars spit out, builds up. And so stars that have a low metallicity, low amount of metals, are older than stars that are highly enriched. Okay, so this is the periodic table, but it's an astronomer's version of the periodic table. Here it is color-coded by where these elements originated from. And so this was created by Jennifer Johnson. And so what you see is that some of elements, as I mentioned, hydrogen, helium, and lithium, came from the Big Bang. That's what we started with. And then all of the other elements came through various other sources. And so what we do with galactic archaeology is we compare very specific elements that come from different places to figure out when did these elements occur in relation to each other. And so specifically, the science question that I'm interested in is this origin equals question mark. This is what my thesis is talking about. So our process is a rapid neutron capture process. And that is like a whole can of worms that we could talk about in a different talk. But all you need to know is that to make the very heaviest elements in the galaxy, you need to have a large amount of neutrons. Because you already have a lot of protons because they're heavy, and so cramming another proton is hard due to their charge. And so it's much easier to add a bunch of neutrons. And so that's why it's a neutron capture process, because we're capturing up neutrons. And it's rapid because this happens in explosions or mergers. There's like a ton of neutrons, and so it can capture many really quickly before it converts those neutrons into protons. The other option is the S process, which is the slow neutron capture process, and that's actually what this yellow thing is. But we know where that comes from. That comes from dying low-mass stars. And so what I'm doing is to study the R process, as I'll refer to it for the rest of the talk. I'm comparing hydrogen, iron, and barium. Now, as my husband pointed out when I gave this talk, barium only has a little bit of orange. And so really, I should look at one of the other ones, because it has a lot of orange. So if you want to study orange, you're picking the wrong element, which is a fair point. I had to tell him that unfortunately it's hard to measure a lot of the other elements, and so I can measure this one. And so that is what I have done. And actually, it's a little misleading. If you measure this one in young dwarf galaxies in the local volume, it's not the same ratio. It has a lot more orange because these dying low-mass stars haven't died yet. And so anyway, so we're comparing these three to study if the R process origin occurred before or after, like early or late, compared to iron, so these exploding stars. And so we know these pretty well, and so I'm trying to study this element based off of what we already know. And so just a point, so I had mentioned gold. So as you see, gold, 95% of gold is produced by this R process, and it's still a very active debate where this R process occurs. And so we're studying the origin of gold, but I'm doing this by actually looking at barium. So we're going to talk about barium, but it's the same as gold. So this is interesting. Okay, so I had mentioned, so metallicity is the iron to hydrogen ratio. So anyway, it's just like how many metals. So higher metallicity means more metals. And so all this plot is showing with this cartoon that my advisor made is that the more time, the more metals. And so this is how we do galactic archaeology, is we say that based off of how many metals I see, because I'm only measuring chemicals, I can use that as a proxy for time. And so I can look back in time. Okay, so I mentioned our process, and I said that the origin was question mark. And so this is what we're debating about. All of scientists in this area have very strong opinions on whether it's from the death of a massive star, so a rare type of supernova, and we've worked it out that this supernova would need to have jets outflowing, and that's where this R process would occur because there's a lot of neutrons. And so this could be a magnetorotational supernova or a collapsar, which sounds very exciting. And so whether it's the death of a massive star or a neutron star merger. And so, of course, neutron star mergers are very exciting right now because they observed a neutron star merger using LIGO, I think almost 2 years ago now. I don't know. They observed it, and it was very exciting. And so a neutron star merger is when you have two neutron stars. And so I've talked a lot about neutrons already, but it's extremely dense stars kind of at the end of their stellar evolution. And when they merge, a whole bunch of neutrons come out. And so they can have our process there. And so the main distinguishing quality, observationally, the main distinguishing quality that I can see is the time scale that these occur. So the theory for these two events is still very flexible. They can still both produce a lot of our process. And so we can't, at the moment, we can't distinguish between it based off of theory alone. And so instead, massive stars live a short amount of time. You know, there's that saying that what burns brightly goes out quicker or something. That's true for massive stars. They run through their fuel very quickly and die very quickly. So from a galaxy's perspective, you would get enrichment from a massive star very early on in your life. Now, a neutron star merger takes a longer time because you need to get stars to go all the way through their evolution, form neutron stars, and then you need to get them to merge, which is actually what takes the longest time because they like to just spin around each other. And so they have to radiate away enough energy in order to merge. Yes?
How long does it take them to merge?
Well, so that's up for debate, but billions of years, potentially.
From how many to how many?
Huh?
From how many to how many?
Well, because it's takes how long for them to merge. It matters how far away they are when they become in a binary. And so the unsatisfying answer is it depends. Okay, so we have massive stars which would enrich the universe in barium early on in the galaxy's life. And then we have neutron star mergers that would enrich later on. And this is what I can probe by comparing barium to iron, because we know the timescales for iron. And so here we have barium versus iron. So we're comparing these two different elements. And we know on what timescale we get iron. And so we're seeing what timescale we would get barium as a function of metallicity. So this is a proxy for time. And so if our process came from the death of a massive star, we would see a negative slope. Now this has become because early on in the galaxy's life, I would get a ton of barium because massive stars happen very quickly. And so I would get a large amount of my numerator. And so I would start up high in this plot. And then as supernovae explode, contributing iron, this ratio would decline. And so the slope actually tells me when barium is contributed compared to iron. So if it was the death of a massive star, I would have a downward slope. But if it's neutron star mergers, I would have an upward slope. And so this is because barium would be contributed later on. And so I would start out chilling over here, and then with time, I would get more barium compared to iron. And so I would see a positive slope instead. And so in my thesis, I measured barium in 250 stars in dwarf galaxies surrounding us, which is a large number for barium. This is very impressive. And a very hard measurement. And so what I can tell you is that for young dwarf galaxies, the R process enrichment is happening at a late time scale. And so I conclude that neutron star mergers are the primary source of R process in early dwarf galaxies. And so if you want to see actual data instead of stars, you can look at my paper, Duggan et al. 2018. Yeah, so this is an example of how we can use galactic archaeology to study something as fundamental as where does gold come from, which we are still debating about. And so to conclude, we've discussed today how galaxies are created, change and die impacts all other areas of astronomy, so everyone cares. And galaxies change so slowly that we would never observe them change in our lifetime. And so instead we use galactic archaeology to study how galaxies have grown since their birth. And we can use galactic archaeology to study what astrophysical source creates heavy elements such as gold. And we have concluded that neutron star mergers are the dominant source of heavy elements in dwarf galaxies when they are young. So thank you so much.
All right. Thank you, Gina, for that wonderful lecture. We have a few minutes for questions. So how this is going to work is that you can raise your hand and wait until I pass around the mic to you so that we can get your question for the YouTube recording. All right. Any questions?
So, what's the biggest change you found in a galaxy when you were studying them?
What?
Like, which galaxy has changed the most when you studied them?
Well, so Fornax dwarf galaxy is this relatively large dwarf galaxy, and it has a dramatic change in barium. That ratio barium over iron that I talked about, it changes substantially, and this is because more than Ursa Minor or Draco or Sculptor, these other dwarf galaxies I looked at. And the reason it changes so much more is because remember when I showed the periodic table, there was that orange stuff that Mark was concerned about. This, oh, it was yellow. This dying low mass star for barium, Fornax had a ton of dying low mass stars contribute lots of barium at the end of its life. And the reason why we saw it in Fornax, whereas we didn't see it for the other galaxies, is because Fornax has a much longer star formation history. It was producing stars for much longer. And that means that we're actually able to see the increase in barium from these dying low mass stars, whereas the other galaxies stopped forming stars. So even though stars ejected enriched material after the stars stopped forming, I can't see those because I'm only measuring the chemical abundances in stars. So the galaxy has to continue to make stars in order for me to see the full impact of their enrichment. So my answer would be Fornax.
All right, it's always nice to have a question from a child. Okay, thank you for coming. So this is the panel Q&A. All four of us are graduate students at Caltech Astronomy. We specialize in different things. So Dylan is a radio astronomer. He knows a lot about supernovae and galaxies. Catherine, well, is also a radio astronomer. She knows about radio instrumentation, cosmic rays, and fast radio bursts. Mia studies star formation and galactic archaeology. Whereas I study exoplanet atmospheres, but I'm mostly going to be passing the mic around. So if you guys have a question, please raise your hand and wait for the mic.
So when I was an undergraduate, I was also interested in all this and ended up as a computer science major, but not as an astronomer. And one of the things that I did as undergraduate work was simulating galaxies interacting with each other gravitationally, but this was some years ago. The computers were slow. It was very hard to make a simulation that was accurate enough. Do any of you guys work with simulations, and are you now able to simulate significantly large enough, massive areas to make them good predictors?
All right, that was a really good question. So the short answer, okay. I'm not a simulator. I do work a lot with simulators, and so hopefully none of them will come after me when I say that personally, I don't think any simulations are accurate. But I do think that for the most part, yes, simulations have improved. So not only probably when you did this work, I don't know what it is. Maybe I'm just making a guess. The simplest way that you can simulate galaxies is by considering only gravity. So if you just put a bunch of particles there, the laws of gravity are pretty straightforward, right? It's just a little bit of math, and you have to repeat it a bunch of times for however many particles you stick in. If you put a bunch of particles together and just let gravity run, that's sort of the basic galaxy simulation. But gravity is not the only thing that operates in galaxies. So what Gina was talking about, stars dying, that's actually a major process. Stars will, over the course of their life, and especially when they die, they'll release a lot of energy into their surroundings. And that can blow out materials from galaxies. That can, cause all kinds of crazy things to happen inside galaxies. So what most of the improvements have been in is this exact thing, including what we call feedback. So the energy and momentum that stars inject, we call that feedback. And so there have been pretty big strides into doing this. So one of the biggest groups that does this is actually, one of the leaders is here at Caltech, Phil Hopkins. He works on something called the fire simulation. And this is sort of one of these new, state-of-the-art simulations that includes not only gravity, but also the hydrodynamics of how gas works, and also all of this feedback that stars produce. The problem with fire and a lot of these really fancy simulations is that, one, not only are they not perfect, they still have to put in a lot of, kind of fake numbers, and they have to make a lot of assumptions in order to get this to work. But they can also really only focus on single or a few galaxies at a time. There are some simulations that have tried to do much bigger volumes of the universe. These are called cosmological simulations. So they simulate huge fractions of the universe, like hundreds, maybe even thousands of galaxies all within one volume. But the problem with that, so the sun, if you take one star and you say that that is the size of a basketball, that was really bad, a pea, maybe? A galaxy is several billion peas. That's a lot of peas. And so imagine trying to simulate everything happening inside a pea and then simulate a billion of those. There's no way you can do that on a reasonable scale. And so the bigger volume simulations, they have to make even more assumptions. So things like how to make stars, they make a lot of assumptions about that. And so I would say that there have been improvements, especially as computing power has improved over time. We've gotten pretty realistic, like these big cosmological simulations, they actually do a pretty good job of making things that look like galaxies. But on the insides, they're probably not quite like real galaxies, and that's because we're fudging a lot of the physics that go into them. That was a super long-winded answer, but I have a lot of feelings about simulations, so I hope that answered them.
She's got one more thing to add, because Mia's not going to plug her own work, so I'm going to do it for her. But like Mia was saying, you can't actually simulate individual stars, right? The simulations, like one star particle might be like 10,000 times the mass of the sun because of your computing requirements. So what you need to do is input sort of physics that observers like Mia discover by using telescopes. And one of the things that Mia works on is she measures the amount of gas in galaxies and compares that to how fast stars are forming, right? And there's a relationship called the Kennecott Law that is widely used in these simulations. Basically, the simulations have no idea like what all the microphysics of forming stars are, but they do know how much gas is in a given volume. So you have a bunch of gas and you just throw in the amount of stars that is spit out by the formula that Mia has measured, basically. And many other people, but yeah.
Yeah, the one thing I have to add to that is from the technical side, which is a lot of the increase in computational speed that we've seen recently. They haven't come from improvements in CPUs. They've come from improvements in GPUs. Because CPUs have not honestly been improving all that much within the past decade or so. We basically topped out in terms of clock speed. Whereas GPUs, people use them for gaming, and they're highly parallel. Because if you can imagine, you have a screen with 2 million pixels, and you want to do exactly the same operation on each pixel. You don't need a CPU, which is very good at like if statements, control logic. You need an embarrassingly parallel processor. Yeah, and that's a GPU. Okay, any other questions?
We're asking that you please ask your questions in the microphone because we're recording so that it can show up on the video.
Gotcha. Yeah. So in the larger session, there was a gentleman who asked about the observable universe through visible light. And I was wondering, how do we know, or can we know, what's behind other stars? When a star is blocking our view of that part of the sky, I mean, are there radio waves? Is there bent light? You see what I'm saying?
So sometimes sometimes the star is massive enough or in the right position that light behind it will bend around it following the shape of space-time from general relativity, and you can see something behind the star. Or even better, if there's a whole massive galaxy lensing the light from galaxies behind it, that's like putting a magnifying glass in front of the distant galaxies. So we can use that as a tool, like a magnifying glass, but stars are, even nearby stars are such small points of light that they don't actually block out large fractions of the sky. So for the most part, you can't see through a star and you can't see through most galaxies, but that doesn't hide a whole lot of the universe from us, because Gina mentioned that she mentioned the word isotropic, which is the idea that the universe is the same in all directions. So if you want to look in a direction and it has a galaxy in front of it, look in a little bit different direction where there isn't a galaxy, and you'll be seeing the same kind of stuff.
Hey, anyone else?
Oh, thanks. Okay, so I'm a summer student this year, working in the IPAC Morrisroe building in the area of the Exoplanet Archive. So I attend these direct imaging meetings every Friday, and there's a lot of terms I don't understand. And so one of them is, so it gets pretty technical with the engineers and the people who work down in the lab. And I'm curious, do you think you could describe to me specifically what an optical fiber is and how it works, how the signal is amplified, how that connects to the CCD, like all of that just bewilders me, and I think it's amazing, but I don't understand how it works.
So that's a great question, and I think instrumentation is really fun. An optical fiber is like a cylinder of glass in a tube that acts as a waveguide, which means it can guide the waves of light down the tube. And so without it, all of your optics has to be set up on a bench, like a flat surface where whenever you want the beam of light to go in a different direction, you put a mirror there. And the air that is in the room has to be super still and not dusty. And so sometimes if you could just put the light in a tube and have it come out the other end, it's much easier to get it into a particular place in the instrument. And you mentioned how it's amplified, which that's something that is sort of the difference between radio astronomy and optical astronomy, in that in optical astronomy you can't very well amplify light, except in there are some exceptions, like a laser where you can amplify a very specific frequency by triggering a lot of atoms to make the same wavelength of light at the same time. But for the most part, with current instrumentation, the light that you just collect from a star, you can't amplify. And so you have to design very sensitive CCDs and very carefully control how the light goes through your system so that you don't lose any of those precious few photons from a star. In radio astronomy, we actually can amplify the waves, and that has to do with the fact that the energy of individual waves is much lower, and there are effectively many more photons per sample, and you can watch the wave go up and down in time.
How small are the individual? The way I see it, and I think I've seen pictures of the individual fibers within an optical fiber unit, and what? How does? I assume there's measures made so that the light doesn't escape as well, right? So what does that look like?
The fibers themselves are maybe 1 millimeter in diameter, and you can measure the loss in the fiber by measuring a certain amount of light going in and measuring some going out. And so sometimes in radio telescopes we want to carry the information farther than we can in a copper wire, and so we'll essentially translate the radio waves into optical light and then later translate it back into radio. So I know some losses for that system, but that could be very different from what you're doing with direct imaging.
Yeah, just one more thing. Catherine can correct me if I'm wrong, but I think that optical fibers are naturally designed so that you don't lose very much light because of total internal reflection. So I don't know if you've taken E&M yet, but when you do, you'll learn about that. And it's just like angles, and whenever your wave hits the boundary, it just reflects back into the wire, and it just keeps on bouncing up and down, going through the fiber. Yeah.
Okay, so I was reading this book in the 50s that was written by Asimov. The science fiction Asimov. Is a science fiction writer. He wrote. It's about astronomy though, and one of the ideas he had was Lagrangian points or something, or Trojan points or something. The Trojan point between the Earth and the Moon can be used to, because it's isolated and it would stay in orbit, could be used to dispose of nuclear wastes. So I was wondering if the validity of that idea, or if anybody's thought of something like that.
Wild. Okay, I certainly haven't heard of using Lagrange points to dispose of nuclear waste. But for anybody who isn't familiar with that term, it turns out that that would be great. So gravity is, in general, very complicated to solve with pen and paper. When there's only two bodies involved, say the Earth and the Sun, it's actually very easy. They're just going to go around each other in some sort of orbit. However, when you introduce a third body, you get all sorts of chaotic orbits. Things will fly everywhere. It's actually a great science fiction book that me and I both love called The Three-Body Problem that talks about this. But anyways, it turns out that in the three-body problem, there... Oh, yeah. I'm not going to spoil anything, as Catherine just asked me. It turns out that in the actual physical, like in physics, the three-body problem, there are 5 special points called the Lagrange points, where if you put a third object, it's not actually going to move relative to the 2 objects. And so I don't remember exactly where they are. One of them is like, yeah, they're there on the other side of the sun, I think. Is there? Yeah, that's right, where it exactly balances out. And so those are the 5 Lagrange points, right? And they're useful because let's say that you want to put something out there and you don't want it to, sort of get thrown everywhere around, say like nuclear waste, or maybe more practically like a space telescope. You don't want to with your space telescope, you don't want to constantly have to like fire your rocket boosters to adjust, its position relative to the Earth and the sun. So you might want to put it out at one of these Lagrange points. And so that's actually what astronomers are doing with the James Webb Space Telescope, for example. It's going to be launched, and it's going to just travel out to that Lagrange point, I think, yeah, L2. And it's sort of just gonna float there and hopefully live for a very long time. Yeah. But the disadvantage of that is that once you're floating out in L2, you're actually very, very far away from Earth. It's very difficult to actually get an astronaut out there to service it. So hopefully nothing breaks, because if it does, it's never getting fixed. I don't know if you heard the story about Hubble. When the Hubble Space Telescope was first launched, it actually had this really bad problem with its optics. I forget exactly what it was. Astigmatism, was it? Or
Spherical. I think it was a spherical aberration.
Okay, yeah. There was a spherical aberration which caused all sorts of blurriness in its images. And so what they had to do is they had to actually send a space shuttle up, and an astronaut actually went out and did some repairs on the space telescope itself, which is really cool. There's, sorry. Yeah. And so you can just look at images before and after, and they're just so much sharper. I definitely encourage you to Google that. Yeah. So
the nuclear waste question, as Dylan mentioned, it would be really hard to maintenance anything that's at one of the Lagrange points. And then the other thing is, just because something gets to a Lagrange point doesn't mean it's always going to stay there. So one of the unfortunate truths is that even in space, over time, you would want something that's super stable for a really long time. And even in space, you can have things like drag. You can have things like, if you send some nuclear waste out there and then try to send some more nuclear waste out there, you can run into things like gravitational interactions, which would send some of the nuclear waste possibly flying where you don't want it to fly. So I think it could be a cool idea, but it seems extremely dangerous, and frankly, I would not want to try with nuclear waste first. Maybe we can try with, I don't know,
Telescope.
of Old Town Road. Something.
WST.
Yeah.
So I have a couple of questions. Reading about the news last few days, they said the star was discovered older than the universe. So I'd like to hear a little more about your explanation of what was discovered, actually. And the second one is we're witness to the TMT saga out in Hawaii. And I'd like to hear from the younger astronomers what you think about that and how it affects your careers and, just from a human point of view.
So let me just go ahead and address the second question.
Okay, hold on. Yeah, let me address the second question first. So the thing is, we don't actually have the authority to speak on behalf of Caltech, let alone the TMT International Organization. So if you want to know our personal opinions about the politics surrounding TMT, you're welcome to come up to us after the event, and I'll be glad to tell you. Right, but for this event, we'd rather focus on the science. Right, for the first question, so I haven't heard about, I read that news story. I haven't dug into detail in that paper. But definitely in the history of astronomy, it used to be that our cosmological models for the age of the universe indicated a universe that was younger than some of the stars. So a famous example is globular clusters. Our stellar models indicated globular clusters that were like 15 billion years old. And at the time, because we didn't know about dark energy or dark matter, we thought the universe was only a few billion years old. Right? And the solution to that is we need to adjust the cosmological model. Now, for this news story, I highly suspect that one measurement is wrong, because we know the age of the universe super precisely, to like within 0.1 billion years. I think it's like 13.6 plus or minus 0.1 billion years.
I mean, okay, so
13.7, okay. Right. No. Oh no. So, do you guys have anything to add?
Oh yeah. So okay. So the way that we measure stellar ages, there are a couple different ways you can do it, but usually the most common way is what's called isochrone fitting, and this is usually easier when you have many stars, but it's possible to do it with one star, although it's questionable. And this is why I think this measurement is likely, as Michael said, it's probably just very uncertain. The error bars on this measurement are probably large enough that it's still consistent for the star to be like as old as the universe. And the measurement itself is probably uncertain or imprecise. So the way that we usually measure stellar ages is by putting them on what's called a color magnitude diagram. So you can measure the color of the star by figuring out its sort of peak wavelength, the wavelength of light at which it emits its peak, like most of its light. And then you can also figure out how bright it is, its magnitude. And by placing it on this diagram and then comparing to different models, you can actually get a determination of the age. This is sort of the roughest way that you can do it. And then you can do more complicated things. You can do what's called astroseismology. So actually using the way that stars vibrate to measure how old they are, which is a complicated thing that I actually don't know how to do because I don't do astroseismology. But all of these methods are pretty imprecise, and they do rely on models that have not been 100% validated. And we're constantly trying to update those models. So I think it's probably most likely, I have seen this story, and I think it's probably that this measurement is uncertain or wrong.
So I remember learning about long baseline interferometry, so you can take telescopes that are radio telescopes that were far apart and effectively get a much larger aperture. And then the obvious question when I was teenager was, well, then why can't we do that with optical telescopes? And I was told, well, we can't because the computers aren't fast enough in the communication between them. And of course, that's all been fixed. And so I guess now we do interferometry with optical telescopes, right? So now the next question is, so when can we do that with amateur instruments?
Some of my friends are working on, which I don't know if necessarily they're looking at interferometry, but they're combining information from surveys and stuff to look for exoplanets. So I know you can do a version of that sort of process like you're talking about. But I don't know.
Yeah, sorry to jump in. Panoptes is not an optical interferometer.
It's not
No, it is similar in that there are multiple instruments, but that's sort of the only way. Actually correlating all the information, Panoptes does not do that.
All right, it's my mistake.
So photons have a amplitude and a phase, which is essentially how bright it is and also what part of a wave cycle you're in. And even in an optical instrument where you think more of photons as individual particles, that information still exists and it's still important. And in order to do interferometry, you have to be able to combine the signals when you still have information about the amplitude as well as the phase. And in a radio telescope, because you can actually sample the wave at multiple points during the wave cycle, you can record amplitude and phase information, save it to a hard disk, mail it across the world, feed it back into a computer, and combine the information even if the telescopes are so far separated that they're not at the same observatory. We can't do that with optical photons because our detectors record the amount of energy of the individual photon, which is similar to only having the amplitude. And so you have to do the combination while you still have the photons. You have to actually combine the streams of photons and then record the result. And that limits how far you can separate optical telescopes. So if you had, it's a really cool to think about if you could build an optical interferometer with amateur equipment, and I bet with the right equipment you probably could, because it's the challenge isn't, or at least in the optical interferometry, it's not so much the computer speed as being able to combine the beams of light before you detect them.
Yeah, so like Catherine was saying, with optical interferometers, you do have to actually use physical mirrors, and you have to have an actual connection. To give you a sense of scale, though, you can think about how often we have to sample the waves coming in. Right? Typical frequencies for radio waves are like gigahertz. So you have to measure something like 1 billion times per second, right? But with optical light, it's like, I don't even know, 10 to the 15 or something like that. And that's just way beyond the kind of clock cycles that we can get with current technology. So you can't just record into your computer.
Yeah, the other thing I have to add is if you have an optical interferometer, as Catherine said, you have to physically combine the light. But that's not all. You have to hold the two telescopes. Let's see. So the length that the light has to travel from one telescope from each telescope to the combination point has to be held fixed to much greater precision than the wavelength of light. And the wavelength of light is like 500 nanometers. So you have to hold the two path lengths constant to much better than 500 nanometers. Now that might seem like it's easy to do, except the Earth is also rotating. So you have to exactly counteract the rotation of the Earth by physically moving the two light beams so that the total path length is the same. And that's very difficult to do, even with professional equipment.
So in the lecture today, we saw like one area of study within galactic archaeology, and I was just wondering what else like in that field is being studied other than, you know, where metals are originating from.
That's a really great question. So I'm super excited about this question. Okay. So Gina talked a lot about barium and how she uses that to determine where metals come from. So I study another element called manganese. So I don't know. I feel like people take manganese supplements. Is that a thing? Okay, maybe I made that up. Whatever. So I use it for a sort of different application, and that's trying to figure out how certain supernovae explode. So there's a class of supernova called a type 1a supernova, and it happens when a white dwarf star, which is what our sun will eventually become, when a white dwarf star explodes. And we know that a white dwarf star is involved somehow, and that's kind of all we really know about these supernovae. They're actually really important because they've been used in Nobel Prize winning discoveries. So this measurement that the expansion of the universe is accelerating, that was done using type 1a supernovae. I think that won the Nobel in like 1990, some year, okay. And so figuring out how these type 1a supernovae explode is actually a really interesting question because we've used them for these applications for a long time, but we don't actually know how they explode. So we know there's a white dwarf involved, but it's not clear how massive that white dwarf is. So sort of the textbook picture that they'll tell you in Astro 101, which I thought for a very long time and turns out is a lie, is that if you get a white dwarf up to a certain mass, it can't support itself anymore, and it just goes supernova because you have enough mass to cause a thermonuclear runaway, like a runaway explosion. But that might not be the case. So a lot of other evidence has come out that there might be other kinds of white dwarf explosions where you have lower mass white dwarfs that maybe they merge, or maybe you can still get just one low mass white dwarf star to explode. So there are a lot of different hypotheses. And so one way to test these is to figure out exactly what mass has to explode. And so people have modeled like different masses of type 1, different masses of white dwarfs that explode as type 1a supernovae, and they find that one of the things that changes pretty significantly is the amount of manganese that the supernova produces. So a really massive white dwarf, when it explodes, will produce a lot of manganese, and a smaller white dwarf, or a lower mass white dwarf, when it explodes, will produce a lot less manganese. And so by measuring the manganese in stars that are living in dwarf galaxies now, sort of the same way that Gina measures barium, I do the same thing but for manganese. And I can actually use that to figure out how much manganese came from type 1a supernovae, and then that'll tell us like whether those type 1a supernovae came from low or high mass white dwarfs. So does that kind of make sense? It's sort of a convoluted, yeah. But yeah, manganese. I'm a fanganese, and you should be too.
Okay, any questions from the back? No? No questions from the back?
Hello. Does our solar system pass through the Orion's arm or with the Orion's arm as we circle around the galaxy?
I don't actually know. Does Mia?
So by Orion's arm, you mean like, so in our Milky Way galaxy, it's a spiral, and those arms have different names, and one of them is the Orion arm. Yeah, okay.
The arms in galaxies are actually waves. Yeah, okay. They're not fixed structures orbiting together. So imagine if you're sitting on a surfboard waiting for a wave, and a wave comes by and it's not breaking, you go up and then you go down and the wave goes by. That's a better way of thinking about spiral arms in galaxies than picturing flows of stars.
So maybe a more direct analogy is like a traffic jam. A traffic jam is not a thing, right? It's just like a place where for some reason all of the stars have bunched up, or all the cars, not stars. And a spiral arm is the same thing. It's like the traffic jam of stars. So the sun is in an arm right now. It's in a traffic jam right now, but it will not always be. Like it'll pass through this area where there's more dense stars, or a larger density of stars. Does that make sense? Yeah, so the traffic jams that are the spiral arms are pretty. They stay around for a really long time. So it won't even dissipate. Like the sun will just go through the traffic jam, and the traffic jam will stay there. Does that make sense?
Yeah. So we actually will pass. We actually will pass through the arm.
Yes. Yeah.
Thanks.
Yeah. Although, wait, I should add that kind of depends on where you are in the Milky Way. So if you're farther out, then you'll move faster than the spiral arm. But if you're farther in, you'll move slower. And so the spiral arm will pass through you. The traffic jam will pass through you on the other side, if that makes sense.
Hey, do we have a question from someone new? No? Okay. Oh, cool.
On the previous one of these, you showed a curve of the velocity versus radius for a galaxy. And is there a corresponding density versus radius for a galaxy? And do these vary from galaxy to galaxy?
Yeah, that's a really good question. Okay, so last time, here, I will just recap for people who were not here last time. Sorry, is this okay? Is everyone okay with me? Like, wait, bye, sorry, what? Okay, bye, son, it's gone forever. Good night. Okay, so last month, if anyone remembers from then, what I drew is something that looks like this. So for a galaxy, the farther out you go in radius, so this is the radius of a galaxy. So let's draw our galaxy here. From the side, it looks like a fried egg. Like you have a bulge in the middle, and you have the spiral bit. So radius, you start here, and you measure outwards. That's the radius. And then here I was measuring the velocity, so how fast stuff is moving around the galaxy. And for a galaxy like the Milky Way, the curve looks something like this. It goes out and it's pretty flat. And this is one way that we started to, it was the first observational evidence for dark matter. Because without dark matter, if you just look at the stars and the gas, the visible stuff in a galaxy, the rotation curve you would expect would look something we're going multicolor now. It would look something like this, and it would fall off eventually. But the fact that, so the fact that we see flat rotation curves means that there's dark matter. So another way that we think that dark matter, well, let me rephrase. So you can actually, yeah, you're right that you can turn this into a density profile for a galaxy. So I'm going to erase these axes and redo that graph. And this time we'll put density here. And this is actually one of the biggest points of contention in a lot of galaxy circles these days. Because what we've run into is something called the Cusp core problem. So sort of the classic picture of this density profile. So if we look at the density of a galaxy going from inside to out, the classic picture is something called an Nfw Halo. It doesn't, there are a bunch of names of people. It's like Navarro, Frank White, some old guys basically who came up with this model. And it looks something like this. So you have a really high cusp of stuff in the middle of your galaxy, and then it decays out over time. Or not over time, as you move out from the center of the galaxy. But one of the problems with dwarf galaxies in particular that we've run into is that for some of these galaxies, they look like they have cores in the middle. So instead of this like cuspy bit going up, they actually have something that looks like this. Sort of a... This thing, so we measure this using the orbits of stuff, like stars in a galaxy. So visible things. But the thing is, the visible stars will actually... The visible stars that we see are interacting gravitationally with everything inside of them, including the dark matter. So this should be tracing everything, including the dark matter.
Okay.
Yeah, so this is one of the biggest problems. How do we get from this theoretical profile to what we actually see? And so feedback, the thing I mentioned earlier, is actually one of the biggest explanations, one of the most, I think, promising explanations for this. So feedback, again, is when stars input a lot of energy into the area around them. And what happens is some of this energy and momentum will actually drag material out of the galaxy. So it'll drag not just gas, but it'll drag so much gas that it can actually pull some of the dark matter out too and sort of flatten out the density profile a little bit. Does that make sense?
Yes.
Yeah. But this is still like an ongoing question. People still argue constantly about whether or not this cusp core problem is a real problem and whether or not we've solved it.
Thank you.
Okay, sorry I talked so much about galaxies.
So I have a question on the sun destiny. A long time ago, it was the theory that the sun will become a red giant, and I've heard you say that it's going to become a white dwarf. How has that changed the knowledge and the predictions over time?
Right, so that was my bad. I did not communicate that very well. So there is the theory that the sun will become a white dwarf, or a red giant, and that is probably still the case. It is after it becomes a red giant that it will become a white dwarf. So all of those things will happen. So what happens is the sun will run out of hydrogen to fuse into helium in its core, and it'll puff up, and that's what causes a red giant. And then the red giant will be fusing helium in its core, and then eventually it runs out of helium, and then it's like, oh crap, what do I do now? So it starts trying to do some other stuff with carbon and nitrogen and oxygen, and eventually our sun is not massive enough to keep fusing heavier and heavier elements, so it'll just stop. And it'll lose all of its outer layers, and it'll just become this like sort of really sad core that cools slowly over time, and that's a white dwarf. Yeah.
Yes, I have a question. What is the methodology for measuring or predicting the density in a galaxy? And where does gravitational lensing come into play?
So you can measure densities by measuring or like overall average density of the galaxy by measuring how much mass is within a certain distance from the center, and you can measure that by how fast the stars are orbiting. What gravitational lensing is useful for is it gives you a very precise measurement of the whole mass of the galaxy that's acting as the lens.
Optical means? I mean, how are you predicting the distribution of dark energy, dark matter, and visible?
Yeah, you use the you observe optically the light from visible stars, and the speed that they're going is a measurement of the gravitational force that they feel, which is sensitive to dark matter as well as light matter. So you can look at the motions of the stars that we see, the light matter, and use the motion to estimate the total of visible matter and dark matter.
I should mention that you're not actually, except for the closest stars to us, you can't actually see them moving on the sky. So what you do is you break it up into all the individual colors, like Gina was talking about during your talk. And specific elements are going to have lines in the spectrum that you measure, in the colors that you measure, that are located at a very, very precise wavelength. And the only reason why that wavelength has a bulk motion or changes is because the star or whatever you're looking at is moving relative to you. So that's how you actually measure the motion.
It's like the Doppler shift that you hear when an ambulance siren goes by.
Sorry, I have another question on Asimov. He has like a short story called Nightfall. I don't know if you've ever heard of it, but it's like a planet that has that's rotating around. It's like a planet that rotates around 7 suns, and I was wondering if like a stable orbit. Well, the gimmick is there's only one night every like 1,000 years or something like that. But I was wondering if there's possibility to have a stable orbit around 7 like stars. I know there's a problem where you can't, the n-body problem or whatever, but I was wondering if it's possible for that to happen, for it to always be day on this planet.
So with pen and paper calculations, you can only do the 2-body problem. For more than that, you need to simulate it on a computer.
Yeah.
And even then, the answer that you get depends a little bit on how fine your resolution of time steps was. So that's a really fascinating problem that's hard to estimate exactly. So I would guess that with the right combination of positions, you could get something that in your computer simulation stays stable for a very long time. But you don't, I believe you don't have a global way to answer that it's stable forever.
It's possible for there to be an actual planet that has that. Oh, sorry. But it's possible.
I don't know, but I would, because I think it would depend on the masses of all the suns, the mass of the planet, and a lot of work to find an arrangement. You would probably, and this would probably sort of feel like cheating, but one thing that might work is put 2 of the suns so close together that the third one is orbiting them so much farther out that it's like it's orbiting one thing.
I'm sorry. And are there actually star systems with like that many stars? Like binary, but like with 7 or whatever?
There are clusters of stars gravitationally bound to each other, but there aren't known planets to be going around all of them.
There are actually systems of stars that are many, many stars orbiting each other. Actually, most very high mass stars are in these sorts of systems. Maybe not 7s, but something like 70% of like very large, massive stars are in 2 or more systems, or like systems with 2 or more stars. I forget exactly what the distribution was, but I think it may, the table I saw may have even gone up to 7. Yeah.
So for some reason, I don't like reading books, but I like reading the Wikipedia summaries of those books. So I've read the Wikipedia summary of Nightfall. I think the premise is that every 3,000 years or something, there's one night on this planet. So I would think that would be very hard to arrange in real life, because if you have multiple stars and you have the planet like wandering chaotically in this system, it's very hard to get something periodic, right? It's possible. I could imagine that like one of the suns. Okay, I could imagine that that like there's one day of night like right now, and then like in 100 years there's some light, but then 100 years after that, it's highly unlikely that that cycle would repeat. Right. So, but we definitely do know planets in multiple star systems. And actually, the closest star system to us is the Alpha Centauri system. That's a triple system, right? There's Alpha and Beta, which are kind of sun-like stars. And then there's Proxima Centauri, which is extremely far from either of those, but it's still gravitationally bound. And that's a white dwarf. I mean, that's a red dwarf. So it's a very small, very cold star. And Proxima Centauri has a known planet, Proxima Centauri b. The interesting thing about Proxima Centauri b is that it could actually be in the habitable zone. Now, that's being pretty optimistic because like, we think red dwarfs are not good environments for life because they have high, the stars are very active. They have high UV and XUV fluxes, meaning there's a lot of radiation that can blow off an exoplanetary atmosphere. And also this planet is pretty cold. Even if all of our assumptions, optimistic assumptions are right, it's still going to be a pretty cold planet. Yeah, but it's definitely possible to have planets in multiple star systems. The other thing that's possible, and actually extremely common, is to have a planet that has a permanent day side and a permanent night side, which is not as interesting as, you know, the scenario in Nightfall. But that happens because the planet is tidally locked to a star. So its rotation period is exactly the same as the wormhole period. It's kind of, well, it's exactly like the situation with the Earth and the Moon. We always see the same side of the Moon. So the same side of the Moon always sees us. And the other side of the Moon never sees the Earth. So if there's people living there, they will never see the Earth. Well, unless they go to the day side. I mean, the near side. Hey, do you have a question for somebody new? No? Cool.
Sorry. I think I was going to say, by the way, if I'm correct, there's that star Albareo, which is at the center of the summer triangle, which we can actually see now that we've looked at. It's like a little blue and a little bit green, and I think it's like part of a sextuple system or whatever they call it, like 6-star system. But I had another question about the instrumentation. So what is an appetizer? And like, how does that relate to, so in these meetings, we're looking at something called a vortex coronagraph, right? And I'm just wondering what the purpose of the appetizer isn't that? I'm sorry, these are very specific questions. I'm embarrassed.
I think the appetizer is, so what a vortex or to back up and give a little introduction to coronagraphy, in order to directly image an exoplanet, you need to block the light from the star that it's orbiting. And if you do that in what seems like the easiest way, which would just be put a dark circle on your, in front of your telescope over the position of the star, you get a problem that light will diffract around it, and you'll still get a lot of light near your exoplanet. And a vortex coronagraph is a way of, instead of just blocking the light with something dark, changing the phase of the light so that effectively all the light from the star goes to the edge of the image, or the edge of the field of view. And then I believe the appetizer is a ring to stop the light blocking the edge of the field of view, but I'm not certain of that.
My understanding of it makes a donut sort of shape, so you can see your
Mm-hmm.
But I was just curious because I've heard the term used in other areas of astronomy of an appetizer, but I just wasn't.
Yeah, so the short answer is that you need fancy ways to block the light from the star in order to image an exoplanet. And I think going deeper into the details is beyond the scope of this, but we can maybe help you find what resources you need to go look if it's something related to your summer project. We're happy to help. Mm-hmm.
Okay, do we have another question?
It doesn't have to be about science. Although, well, you can ask us about like what it's like to be an astronomer, which is not really.
Yes, but something science related.
Something, yeah, related to astronomy would be ideal.
What causes a planetary body or any other celestial body to become tidally locked?
That's a good question. Michael, do you want to take it?
Okay, sure. What causes a body to become tidally locked? Okay, let's see. Number one, whether I can remember, and number two, whether I can draw it. Okay, where's the marker you used? Goodbye, Galaxy.
Yeah, so here we have a sun or a star and a planet that's very close to the star, orbiting around it.
Damn, okay, let's see. How do I depict this?
So because of the size of the planet, because it's not just a point mass, the side of the planet that's facing the star feels a slightly different gravitational force than the side of the planet away from the star. This is the origin of what we call tidal forces, because these small differences across the size of the planet can distort the shape of the planet, that can cause a torque that means that different spin configurations with respect to the star that it's orbiting have different total potential energy levels. And all of these orbital mechanics questions involve finding stable configurations are the configurations that have the lowest potential energy. If you hold a brick above the ground, it has more potential energy than if it's sitting on the ground. If you let the brick go, it's going to go to a lower energy configuration. It's going to fall. And in the case of planets orbiting a sun or the moon orbiting the Earth, the lowest energy configuration is to have one side always facing the thing that it's orbiting. And these small tidal forces will exert torques to change the spin until it stays in that stable place.
Yeah, so okay, hold on. Let me explain this diagram first. So I'm not very good at drawing. That's why it took me so long. But here's the Earth. Here's the Moon. Gravity, the strength of gravity falls off with distance. The further you are from the Earth, the less you feel its gravity. So this side of the Moon, the near side of the Moon, feels more gravity than the far side of the Moon. And that tends to stretch the Moon. Right, so that stretches the Moon into a slightly elongated shape. This is highly exaggerated, but you get the idea. Now, the Moon is doing two things. It's orbiting the Earth like this, and it's also rotating. So now let's suppose that the moon is rotating faster than it's orbiting the Earth, right? So the moon is rotating, but faster than it's orbiting the Earth. So if it was rotating at exactly the same rate, by the time it comes here, the elongated axis will be facing the Earth, like this. But because it's rotating faster, the elongated axis is pointed away from the Earth, right? It's like this. So then what happens is the Earth pulls on this side of the elongated moon more than it pulls on this side of the elongated moon. And that tends to rotate the moon in this direction. Now, what's significant about this direction, namely clockwise? Well, it's opposite of the initial rotation of the moon. It's also opposite to the initial orbital direction of the moon. So this tends to slow down the rotation of the moon. Right, okay, so to recap, if the moon is rotating faster than it's orbiting, then the Earth's gravity tends to slow down the rotation. If it's rotating slower than it's orbiting, then you can imagine this ellipse is elongated the other direction, and the Earth tends to speed up the rotation of the moon. And like, where does it come to a balance? It comes to a balance when the orbital period and the rotation period are exactly the same. Yeah, so that's the physical mechanism that tidal locking actually occurs by. Yes, so the moon has already become tidally locked to the Earth. Now the Earth will also become tidally locked to the moon. The sun? Okay, so the question is the Earth going to become tidally locked to the sun? The answer is no. We're way, way too far away. But if we were closer, so we do know of many planets that are very close to their stars, and we know for a fact that they're tidally locked to their stars. These are typically, so at least for planets in the habitable zone, these are around small stars. Why small stars? Because with small stars, the habitable zone is very close to the star. For our sun, it's like, it's 150 million kilometers away from the sun. And the tidal force goes down as 1 over distance cubed. So it's very, very sensitive to distance.
If I remember correctly, I think the time that it actually takes for two bodies to become tidally locked to each other goes as the distance to the 7th power. So basically, if something were to take 10 years to become tidally locked, and you make it 10 times farther away, then it would take like 10 million years. And so the Earth is really far away from the sun, much, much farther away than the moon is from the Earth. Yeah. And so it's eventually going to be tidally locked, but it's going to take an absurd amount of time. I think we had a question from person in the green shirt.
Yeah. Okay. Hold on. Sure.
You were asking about kind of non-scientific questions, and I guess I have some that, Michael was mentioning before. We still need to represent, acceptably before Caltech. So maybe some things about interaction within the scientific community and things aren't quite appropriate, but maybe this falls on the right side. You have behind you lists of your specialties, and I'm curious. I mean, I'm thinking about how in medicine or even in undergraduate majors how we select, and I'm wondering about how is it that you selected yours, or how those in your profession select in general.
Yeah, so this sounds like a question that maybe all four of us will just attempt to answer for ourselves. So I guess, how did we decide on our specialties? Is that the question? I mean, personally, I didn't really. I mean, so the way that I got into astronomy was that, I had no idea I wanted to be an astronomer when I went into college, but I just took like an intro to astronomy class taught by a wonderful professor, Phil Choi, at Pomona College, and he saw that I was just really interested in his class, and he was like, "Oh, I know of like a summer opportunity where you could do some research," and he said, "Maybe you should apply for this." And so I decided, yeah, I need a summer job, so why not? And I got the job, and that's sort of just how I started with radio astronomy. That was the one project that was available. It was actually extremely difficult to start out with because what happened was my advisor, who is awesome, except at the time didn't know all that much about radio astronomy, just decided, I have all this radio astronomy data from the Very Large Array, and I don't know actually how to process this data. Here, summer student who just graduated or just finished your freshman year, please learn how to deal with this data and take this burden off my hand. And so that's like sort of how I got started. I flailed around for like a month, getting absolutely nothing done, as is the case with many summer students. I don't know if you relate. But then he sent me off to like one of his collaborators in New Mexico, who's a wizard with being able to process data from radio interferometers, and I sort of got to learn from the best. And eventually, I just built up enough expertise in radio astronomy where like this is sort of my wheelhouse now. Like if you have a question about like how you can do observations specifically with the continuum with the Very Large Array, like I know a lot more than most astronomers do about this particular like very niche subject. And so that's sort of how I got my specialty, right? It's like I know how to do this technique really well. Now, what like kinds of scientific questions can I apply this to? And it turns out that star formation and supernovae are two interesting ones. Certainly not the only ones that you can do with these sorts of techniques, but ones that I both have the skills to do, and also, there are people interested in it, and also people here at Caltech specifically who are interested in it and who I can work with. And so it's sort of just like happenstance.
So for me, I know that I like building things, and so I wanted an experimental project where I'm actually building an instrument and measuring something with it. And as an undergrad, I spent a summer at Virgo, which is a gravitational wave interferometer, sort of like LIGO. And there were a lot of things I loved about that work, but I realized that for my PhD, I wanted to work with a small team of people on a small instrument where within my PhD, I could build something and observe the universe with it, whereas LIGO took decades and thousands of people to do. So I knew I wanted to find a project where I could answer a science question I was interested in and build something. And then radio astronomy has the other advantage that it includes a lot of signal processing, which has some math problems that I enjoy. And the components are, because the waves are sort of human scale, the electronic components are also sort of human scale. You don't have to be in a clean room that takes a while to put all your gear on in order to go in and specially filter the air so there's not a grain of dust. I enjoy radio instrumentation because it can go out in the desert, and you want to be out in the desert to be away from people's cell phones and stuff, but you can go out in the desert and put some components together and start to, and climb on them. And so the science topics that I'm interested in are cosmic rays and fast radio bursts, which are connected by the fact that they both involve problems where you need to be able to measure radio waves from the sky that are changing very, very quickly. A lot of astronomy involves looking deeply at something to collect light for a long time to see a very, very faint object. But if you're interested in the things that change in the universe on the very fastest time scales, you need a completely different kind of instrument that maybe can't see as deeply, but can see something that only lasts a millisecond in the case of fast radio bursts, or tens of nanoseconds in the case of cosmic rays. And so so cosmic rays are high energy protons or neutrons for the most part that can't get through our atmosphere, but when they collide with the atmosphere, there's a shower of radio waves, and that's how we can try to observe them. They come from the highest energy environments in the universe, and it's a challenging problem to figure out what things are out in space that could accelerate something to those energies. And collecting more of them is a way to start figuring that out.
So I think my answer is similar to Dylan's in that it was pretty much happenstance, but it was happenstance that happened because of a lot of different things that I tried. So when I got to undergrad, I knew I liked physics a lot, and I was like, all right, I'm going to be a physicist. I'm probably going to be a particle physicist. I might end up working at CERN. Maybe I'll be the director of CERN. You never know. And when I got to undergrad, I was like, okay, so I'm not going to get to CERN right away, so I need to try some other things. So I tried a lot of other things. I tried computational astrophysics, which was writing simulations of supernovae and galaxies and other things. And I was like, actually, I hate this. Because I don't like writing code into this black box that just spits out physics. Like, it's fake physics. You're not looking at real data. This isn't real. So I thought that was kind of ridiculous. Sorry, wow, okay. I feel like that was maybe very harsh. I didn't like it. It was not for me. Also because the simulations kept breaking and there was this whole debacle where I forgot to put a semicolon and then wasted several hours of valuable supercomputer time. Anyway. And then I tried working in a lab. I did like a material science, like soft matter physics kind of thing, and broke things, realized I was just not suited to work in a lab, and also the basement lab was cold, and I was lonely, and I wanted sunlight. This was just not a very good environment for me, I think. And then I tried particle physics. I did work at CERN for a couple summers, and after 2 summers, I was like, wow, I actually don't like this. And I had this existential crisis, like, who am I if I'm not going to be the director of CERN? What am I going to do? And then I found astronomy, and I found galaxies in particular, and I just thought galaxies were super cool. So all of the stuff that I do, I mean, they're kind of random. Like galactic archaeology and star formation are related but pretty different facets of just trying to understand how galaxies work. And I just realized I like galaxies. I like observing galaxies. I like working with the real data. Work and analyzing and trying to interpret data is really fun to me. It's like a puzzle that you get to put together. And galaxies are just super cool because they're like stars but more, because you have billions of them. And they're these ecosystems that change over time. Like you have the stars and gas interacting with each other and galaxies interacting with each other, and I just thought that was super cool. So I was lucky enough to find really good advisors and have really good projects in galaxies, and I think that's kind of why I ended up there. Maybe if I had started doing astronomy in a different field, maybe I would have ended up doing planets or cosmology. I probably would not have ended up doing cosmology. I don't like cosmology.
Right, okay, so that leads very well into what I do, which is exoplanets and cosmology. Well, so yeah, I still don't know what I want to do with my life. It's probably not being the director of CERN. But yeah, what it is exactly, I don't know. Yeah, so the way I started out in astronomy is that I was a freshman in college. And I needed to find something to do for the summer, right? Do I get a job? Do I get an internship? And I decided I wanted to do some research. And at that time, I'd already taken a few physics classes, but I wasn't basically qualified to do anything. So I looked around and was asking myself, which labs would take a freshman student who doesn't know much? And that turned out to be the cosmology lab. They were always looking for people. So that's what I joined. I joined a cosmology experiment. But I don't think that's the only reason, because I think I liked cosmology at that point. And that's because, for those of you who don't know, cosmology is the study of the universe on the biggest scales. So cosmologists ask questions like, how old is the universe? How big is the visible universe? What is dark energy or dark matter? What is the distribution of matter in the universe? Right, so yeah, the study of the universe at the biggest scales. And those are profound questions, right? They're important questions. I think they're questions that many people ask, even people who have never heard of cosmology and don't know much about astronomy in general. Yeah, so working on that gave me a lot of satisfaction. So in my junior year, I had to do an independent research project. And this time, I had basically full freedom to choose who I wanted to do it with. Well, assuming they wanted me, assuming they had space. But at that time, I also had no idea who wanted me and who had space. So my idea was choose a field I like, go find people who work in that field, and ask to do a project with them, right? And At that time, it was shortly after Kepler launched. Shortly after Kepler began producing results. So for those of you who don't know, Kepler is a spacecraft whose goal is to take a statistical sample of exoplanets. So discover thousands and thousands of exoplanets in a systematic way so that we can quantify how many planets are this big, how many planets are this far away from the star, how many planets have this orbital period, and so on. Right, so that's the scientific answer. The scientific objective of that mission. The romantic mission of that, the romantic objective of that mission was to find an Earth-like planet around a Sun-like star at an Earth-like distance. So basically, find an Earth analog. And that was an important question at the time because we didn't know how common Earth was in the universe, right? And without knowing even how common the Earth is, how do you answer questions like, is there life elsewhere in the universe? Like how common are intelligent civilizations? So the first reason I chose exoplanets was because it was making a lot of progress. Second reason is a very interesting question, right? Probably everybody has wondered whether there's life out there. Everybody has wondered like how common we are in the universe. And the third question, the third reason is that there happened to be a professor who was looking for students who had an interesting project. And that person happened to want somebody who's good at, who's interested in programming. And like at that point, that was also one of my interests. So I was like, yeah, sure, sign me up. And that's how I ended up in this field.
So I think we have time for one more question. Yes.
Okay, hold on. Before that, is there anybody who hasn't asked a question? Okay, you get the last question.
Okay, I have another question about Asimov. So, in the book, it was written in 1959, and I guess they didn't know what Jupiter was made of. So he said that Jupiter was probably a big ocean. I know he's not an astronomer, but he said there was probably a big ocean, and there was probably in fact life on Jupiter because there's like ammonia in that, and like whatever. There's like whatever Earth looked like when it was young, it was in the Jupiter atmosphere. But when the book was published, it was actually liquid metal hydrogen. So he had to like write an addendum saying, "Oh yeah, I was wrong." But I was wondering, how did they figure out what the inside of Jupiter was made of? If it was spectroscopy or something like that? Yeah.
I think you can measure densities of the planet from its interactions with from the things orbiting it. You have from images an estimate of its radius, and then if you can measure its mass, you've got an idea of the density. And so I think as a first order crude estimate of what it's made of, you can start by finding how dense it is. Do you want to add anything?
Yeah. That's very true. If you know how massive the planet is, you know how big it is, you calculate its density, and you find, this can't possibly be rock. But I think even by the 1950s, we had pretty detailed spectra of Jupiter. And if you have detailed spectra of Jupiter, you can know something about its composition. The thing is, hydrogen is actually doesn't have a lot of spectral features. So I don't think they could directly measure the presence of hydrogen. So I don't know how they figured that out. But my favorite method of measuring the composition of Jupiter, I think this was done in 1960s. You take a spacecraft, you go there, you go into its atmosphere with an instrument and a parachute, and you make it report back the composition of the atmosphere until it dies. Why does it die? Because it's crushed by the overwhelming pressure, and it's melted by the overwhelming heat. So yeah, that happened with the Galileo probe. And after that, we know for sure that the atmosphere is hydrogen, helium, and there's some ammonia, there's some methane. Yeah, we know the composition really well by now.
is there possibility of life? I was just kind of wondering, would there be possibility of life on like a gas giant type planet, or like a planet that's much bigger than Earth, like with a much greater gravity?
Okay. Is there a possibility? Yes. Is it likely? I would say no. Because one of the things that I think is really important for life, and by the way, I'm speculating. Nobody knows the answer. One of the things that's really important for life is you have liquid water, and you have some way of evaporating the liquid water so that you can concentrate whatever molecules are inside. So once that happens, the molecules can find each other. They can form longer and longer compounds. And carbon molecules can grow absurdly long. And that's possibly the precursor for life. So if you have an atmospheric, a gas giant, there's no solid surface, there's no place for water to be. I don't think there's a way for life to get started. Okay, so unfortunately, it's already past 10, and we're out of time. If you have any more questions, feel free to come up to us afterwards. Otherwise, have a nice night, and thank you for coming.